Okay. So we know that we need to report the SN curve for a material to be able to calculate the endurance limit, SE, which corresponds to the plateau at beyond أو أكتر من 10 to the power 6 cycles for steel, and for other alloys such as aluminium alloys that do not have a constant plateau, the endurance limit was agreed to be the fatigue strength that corresponds to 5 في 10 أس 8 cycles. Okay. All these testing was done in a lab under ideal conditions تحت ظروف مثالية. لذلك we need to ان احنا نضرب الانديورنس ليميت ده في مجموعة factors لكي نحاكي ما يحدث في real applications. So this S-E is the one that is reported from laboratory experiments, where this is the SE that should be used in design problems. So the S-E that is taken from the SN curve should be multiplied with these parameters. Ka, for example, is the surface condition factor. العينة اللي اختبرت في المعمل كانت عينة السيرفيس فينش بتاعها مثالي، ولكن this should not be the case for all applications. فال Ka accounts for أو بيأخذ في اعتباره السيرفيس condition. Kb is the size factor. العينة اللي اختبرت أيضا في المعمل لها أبعاد قياسية، ولكن الأبعاد في الريل لايف applications مختلفة. فإحصائيا statistically كل ما الجسم بيكبر كل ما كمية الديفكتس اللي فيه بتزيد. So Kb accounts أو بيأخذ في الاعتبار السايز factor. Kc is the load modification factor. العينة اللي اختبرت في المعمل عشان أجيب ال SN curve كانت اختبرت تحت rotating bending. So the main stress acting is bending. What if is the fluctuating loads is not in bending, it's in axial loads or in torsion loads or torsion moments. Okay, so this accounts for the type of fluctuating stresses. Kd is the temperature modification factor. العين اللي اختبرت ايضا في المعمل كان تحت درجة حرارة 20 او 25، لكن في الريل لايف ابلكيشن ممكن جدا الفلكتويتنج لودز دي تكون موجودة على components بتتعرض لدرجات حرارة عالية 200 درجة let's say. Ke is the reliability factor. How much يعني how much serious the application is it related to the life of people, all right, of human beings. So طبعا كل ما الكومبوننت اللي بيتعرض للفلكتويتنج لودز بيبقى جزء من ماكينه بتعرض حياه بني ادمين لخطر، فالريابيليتي بتاعته لازم تبقى عاليه. For example, in aviations, for example, the reliability can go to numbers as 99.49%. Kf are miscellaneous factors, okay, ودي بقى بتشمل اشياء كثيره ولن تؤخذ في اعتبارنا الا لو ذكرت في راس السؤال ان take the miscellaneous factor to be as such. Take a value for Kf, for example. Okay. So let's talk about all these parameters in details ونشوف ازاي نحسبها. For example, this is the surface condition factor Ka. هيحسب من خلال هذا القانون. A as ultimate أس B. A and B are two constants. ال A وال B دول لازم تميزهم عن ال A وال B اللي احنا خدناهم قبل كده في القانون بتاع الفاتيك سترينث والنمبر اوف سايكلز تو لاين اللي هو SF بتساوي A N أس B. ال A وال B دول غير ال A وال B اللي هم قدامك في المعادلة دي. تمام. They're totally different. These A and B values are taken from this table. So this table will have to be given to you. هديهولك. Based on the surface condition, if it's ground surface, machined or cold drawn, hot rolled as forged, this A value will be taken and this B value for the exponent will be taken. Okay. If you're working in megapascal, and here if you're working with kilopound per square inch. So you need to be careful. So A S ultimate أس B, and your S ultimate will be in megapascal if you're working with these. Okay. B, for example, is the size factor. So there are certain equations here. If your diameter is within this range of inch, within the inch, you will use these two equations. If you're working in SI units and your diameter is in between these ranges, these are the equations to be used. Okay? For axial loading, there is no size effect. So for axial load, if the fluctuating loads are axial, your KB value will be equal to 1. For the size factor, you would need to ask yourself a question. Is your component rotating or stationary؟ هل الجسم بتاعك اللودز اللي عليه ثابته لكن هو نفسه بيحصل له روتيشن فبيتعرض ل fluctuating stresses due to its rotation but the external loads are constant، ولا ال component is stationary and the external loads are fluctuating. Okay? For non-rotating shapes, you would need to calculate the equivalent diameter. For example, if your core section is circular, your equivalent diameter would be 0.37d. If it's rectangular, it would be 0.808 square root of hb, and so on. Okay, let's take an example for calculating kb. A steel shaft loaded in bending is 52 millimeter in diameter with abutting a filleted shoulder of 38. يعني عندي one shaft with two diameters 52 to 38 وبينهم في fillet. The shaft material has a mean ultimate tensile strength of 690 megapascal. Estimate the marine size factor Kb if the shaft is rotating or non-rotating. If it's rotating, you would simply check your 52 millimeter lies within which range of an equation, and you use that equation to calculate Kb. Okay? If it's non-rotating, you would calculate the equivalent diameter, 0.37d, and then you would check this equivalent diameter lies within which range of an equation. You have two equations. فهتشوف ال 19.24 وقع في أي نطاق لأي معادلة وتستعمل المعادلة دي المناسبة لحساب الكيبي. KC, for example, as we said earlier, your S-E or your endurance limit was already calculated in bending. Okay? So if your fluctuating mode is still in bending, you would not need to مش هتحتاج ان انت تعمل modification لل S-E. So if your fluctuating loads are in bending, your KC, which is the load modification factor, would be 1. If the fluctuating load is axial, KC would be 0.85. And if the fluctuating loads are in torsion moments, it would be 0.59. So see how crucial changing the loading mode would be. خلاص؟ يعني ايه 0.59؟ يعني هيشيل almost 41% من قيمة ال S-E if your fluctuating loads are torsional. So it's very important to account for what type of loads are acting. And then we go to the temperature factor, KD. Okay? Here for accounting the temperature effect, there are two routes. هناك طريقين ولا يجب أن تجمع بينهم. يعني يا تمشي في السكة الأولى يا في الثانية. السكة الأولى إن أنا هديلك تيبل. التيبل ده مديلك certain temperatures and a certain ratio. Okay? خليني أشرح لك إيه الريشيو دي. These values are the ratio of the ultimate tensile strength at that particular temperature divided by the ultimate tensile strength at room temperature. So ST divided by SRT. Again, this is the ratio of the ultimate tensile strength at this respective temperature divided by the ultimate tensile strength at room temperature. Okay? Route number 1. If you see a service condition temperature, for example, of 200, you would take this value of ST divided by SRT of 1.02, and you would multiply your ultimate tensile strength at room temperature by this ratio of 1.02. You would achieve the ultimate tensile strength at this respective temperature at 200. بعد ما جبت الالتيميت تنسايل سترينث عند ال 200 درجه مئويه هتضرب الالتيميت تنسايل سترينث دي في 0.5 لايجاد الانديورنس ليميت الكوركتد انديورنس ليميت at 200 degrees Celsius. Okay, so if what is known to you is the ultimate tensile strength at room temperature, you would go with this route and use this table to calculate this ratio. Okay? طيب هنلاحظ ان الفاليوز دي يعني for example let's say at 20 degrees Celsius which is room temperature, the ST over SRT is 1. As the temperature is increased, this ratio increases, and then when the temperature go beyond 250, this ratio will start decreasing. This increase is a phenomena in carbon steels known as strain aging. Okay? It's a phenomenon that does not happen in all type of steels, of course, or all type of materials. If again root 1 هو لو انت عارف ال ultimate tensile strength at room temperature، هتروح عند التمبريتشر المذكور عندك اللي هي السيرفيس تمبريتشر اللي هي هيتعرض ليها الكومبوننت وتشوف الريشيو دي كام. هتروح من الريشيو دي والالتيميت تنسايل سترينث ات روم تمبريتشر هتجيب الالتيميت تنسايل سترينث عند التمبريتشر المذكوره. بعد كده هتضرب هذه التنسايل سترينث عند التمبريتشر المذكوره في 0.5 لايجاد الانديورنس ليميت. This is root 1. Let me tell you about root 2 now. Root 2, if what is known at room temperature، لو المعلومة لديك المتوفرة لديك هي endurance limit at room temperature, you would go with root 2. عندك معادلة جاهزة. This temperature is in Fahrenheit, by the way. Okay, so you would need to transform the Celsius to Fahrenheit and then apply in this equation, and then you get KD. Once you get KD by substituting into this equation, you would multiply KD by the endurance limit at room temperature, which is already known to you. Okay? فده root number 2. Let's take an example. Okay? Let's read the problem together. A 1035 steel has a tensile strength of 490 megapascal and is to be used for a part that sees a service temperature of 230 degrees Celsius. Estimate the marine temperature modification factor and SE at 230 degree if what is known to you is the room temperature endurance limit. لو المعلومة المتاحة لديك هي ال endurance limit at room temperature 270 megapascal. ده الطلب الأولاني. الطلب الثاني if the tensile strength at room temperature هي المعلومة المتاحة لديك. Part A. If the endurance limit at the room temperature is the thing that is known هي المعلومة المتاحة لديك هتروح تحسب الكي دي. المعادلة اللي قدامك دي هي معادلة صالحة للاستخدام بالتعويض بالسلسيوس right away، مختلفة عن المعادلة الأولى اللي أنت شفتها بالفahrenheit. The 230 is the degree in Celsius. So this is the constant plus another constant في T اللي هي surface temperature in Celsius minus another constant في T squared plus another constant في T cube minus another constant في T أس 4. All these temperatures are in Celsius already. So this is the KD. You would take this KD and multiply by 270 and then you would achieve the SE. This is the corrected endurance limit corrected for temperature effect. طيب النقطة الثانية لو المعلومة المتاحة لديك هي ال ultimate tensile strength at room temperature. فهذه الحالة you would use the table that I've just shown you. هتروح عند 230 درجة مش هتلاقيها، لكن هتلاقي عند 200 و 250. فهتعمل linear interpolation to get this ratio. So ST divided by SRT is 1.0197. You will use this ratio to correct for the tensile strength at room temperature. So هتضرب ال 1.0197 في ال ultimate tensile strength at room temperature which is already known and given to you. هنا هتجيب ال ultimate tensile strength عند ال service temperature اللي هي 230 درجة مئوية. هتاخد دي تضربها في 0.5 لإيجاد ال endurance strength. اوكي؟ طبعا عارفين احنا موضوع ال 0.5 ده ان for steel alloys the ratio between S endurance to ultimate tensile strength is 0.5. So you know, and there is a limit. this equation is valid. يعني ال S dash E is equal to 0.5 S ultimate until an S ultimate of 1400 megapascal. Once the ultimate tensile strength reaches أو exceeds this value, بيعلى عن 1400, then the S dash E takes a constant value of 700 megapascal. And we have already discussed this before. So you either go with this route or with this route, but you don't combine the two routes together. Now this is the KE, which is the reliability factor, and for KE to be taken into account, I will have to give you this table. Okay, this is the reliability, of course, that is related to the type of application. يعني this is an application that is not very crucial, مش مهم خالص. So you don't modify the value of S dash E. KE is 1, and this is the value for, and this is the reliability value for a part or a component that is in a crucial machine. Okay, so this is 0.62. See how much you take off the S dash E. هنا انت you're taking around 38% off من the endurance limit that was calculated from the SN curve that was achieved inside a lamp or معمل يعني. Okay, the last modification factor is KF, which is called miscellaneous effect factor. هذا KF بيشمل أشياء كثيرة. Okay, I will leave for you to read through it. هذا KF will not be taken into account في المسائل بتاعتنا إلا إذا نص عليه في رأس السؤال واديتك الفاليو بتاعت KF. ف if not, then KF is equal to 1. لو هي مش مذكورة في رأس السؤال, then you would have to assume a KF of 1. Let me just explain this picture for you. ده beam عملت له case hardening. Remember the word case hardening من الديفيوجن بتاعت material سنة أولى. Okay, this is the core and this is the depths that was case hardened, ودي السماكة اللي عملت فيها case hardening. So this is the value of the endurance limit of the core من هنا لهنا, and this is the value for the case. This is the endurance limit for the case. Okay, and if this part is subjected to bending, then this would be the distribution of sigma, 0 on the neutral axis and maximized at the outer fiber. Okay, look at where this stress exceeds the endurance limit and the interface. Usually the problem with case hardened components is would be at the interface between the case and the core. شايف السيجما هنا تعدت قيمة الendurance limit عند المنطقة اللي بيلتقي فيها الكيس بالكور. This is where the problem usually originates من هنا. هنا في miscellaneous effects, corrosion. If the body, if the component that is subjected to fluctuating loads is inside a corrosive media, like seawater for example, لو عندي mean stress موجود, alternating stresses, concentration بتاع الالكترولايت, لو الجسم المتعرض للfluctuating loads موجود في محلول بيمرر كهرباء وفي concentration لأيونات معينة فيه, dissolved oxygen, temperature, material composition, cyclic frequency, fluid flow rate around specimen. هنا مثلا for example الستيل structures اللي في الاوفشور اللي موجوده, هل هي موجوده النهر اللي بيحدث عليها نتيجه حركه المياه حواليها, هل حركه المياه سريعه بطيئه, اللي هي الفلويد flow rate. So these are all considered inside the KF or the miscellaneous effect factor. Another factors you can read through it. كل ده داخل جوه الكياف. Okay, so a new topic now, stress concentration. Components that have geometrical discontinuities will always be subjected to stress concentration. Okay, what do I mean by a geometrical discontinuity? أي جسم في عدم اتصال للشكل الهندسي له, ده هيسبب أن يحدث تعاظم لقيمة الإجهادات في المنطقة المحيطة بهذه geometrical discontinuity. Let me define this term in more details. A geometrical discontinuity, for example, just like this hole, الهول ده انا ممكن اكون انا اللي عامله في البليت. This is a plate with a hole عشان احط فيه مسمار later on to be assembled on another component في مكنه مثلا. اوكي. هذا المسمار او هذه الفتحه this hole is considered as a geometrical discontinuity عدم اتصال الشكل الهندسي مما سوف يسبب stress concentration around this hole. This stress concentration is defined through a parameter called KT and it's termed as the stress concentration factor which is defined as sigma maximum divided by sigma net. Sigma maximum is the maximum value of stress in the vicinity of this hole في المنطقة القريبة جدا من هذه الهول على nominal stress value في منطقة بعيدة تماما عن هذا الهول. Okay, so KT gives you how much this nominal stress sigma will be magnified in the vicinity أو في المنطقة القريبة جدا من هذا الهول. Okay, so this is KT, the stress concentration factor. And to be able to get the KT, you will be calculating KT through such figures. I will be giving you a figure that will be self-explained. يعني بصورة بتوضح ازاي تستعمل هذا الفيجر وتجيب ال KT. For example, this is a plate, okay, with a width of W. The diameter of the hole is a D. So you will go into calculating D على W, and for a certain D على W, هتروح تجيب ال value of KT. Okay? As you see here, KT can reach a value of 3. Okay? When the whole diameter becomes very small compared to the width, this is which exemplifies ده زي كأنه بيحاكي وجود very sharp crack inside the plate. شايفين ال KT can take a value of 3. So this means that في المنطقة القريبة جدا من هذا الهول الصغير the stress will be magnified by 3 times. يعني لو في المنطقة البعيدة هنا 100 ميجا باسكال هيبقى around this hole 300 ميجا باسكال. So taking into account KT for any geometrical discontinuity is very important and crucial in fatigue loaded components. أقولها تاني بالعربي. لازم في الأجزاء المعرضة لفاتيج and dynamic loads لو هذه الأجزاء فيها geometrical discontinuities عدم اتصال للشكل الهندسي بها فيجب أن يؤخذ في الاعتبار الإفكت بتاع الستريس concentration من خلال أخذنا في الاعتبار الفاليو of KT عند النقطة أو عند المنطقة اللي فيها geometrical discontinuity. In the next slide I'll give you some more examples about these geometrical discontinuities. For example ده المثال بتاع اللي كان موجود هنا عندنا نفس المثال plate with an internal hole but instead of axial load عندي bending. هنا notch with a fillet radius. Okay. هنا of course this is an axial load. هنا أيضا notch with a fillet radius but in bending. عندي this is a very common problem in shafts. Usually shafts in gearboxes are made up of stepped diameters. يعني عندي diameter كبير بيروح على diameter صغير through a fillet of R. This is if the shaft is subjected to axial load and this is if the shaft is subjected to bending and so on. So we have many of these curves that covers all types of geometrical discontinuities and all types of loads. Alright? طيب هل كل الماتيريال بتتأثر بوجود الجيومتريكال ديسكونتينيوتي دي بطريقة متساوية؟ لا. في ماتيريالز التفنس بتاعتها بتقلل من شعورها بوجود هذه الجيومتريكال ديسكونتينيوتيز. That's why they came up with another parameter called fatigue stress concentration factor. Okay? It's KF. ومبدئيا كده قبل ما نتكلم في هذا الفاكتور يجب أن تكون قادر على التفريق ما بين هذا ال KF which is the fatigue stress concentration factor and KF اللي هو Miscellaneous effect factor اللي اتكلمنا عليه سابقا to modify the value of S-E. These are two different things completely. خلاص؟ طيب ال fatigue stress concentration factor ده KF is a reduced value of KT. هو قيمة مصغرة من KT. Which means that إن أكبر value للKF هي KT. طيب KF ده عبارة عن إيه بقى؟ This is the maximum stress in notched specimen على the stress in a notch 3 specimen. ده أقصى قيمة للإجهاد في عينة تحتوي على نوتش على قيمة الإجهاد على عينة مصنعة من نفس الخامة ولكن لا تحتوي على أي نوتش. خلاص؟ طيب من هنا طلعنا بارامتر جديد اسمه notch sensitivity small q. It's kf minus 1 على kt minus 1. This is for normal stresses and kfs minus 1 over kts minus 1 if you're talking about shear. So k for normal and k for shear. This of course covers axial and bending, and this of course covers shear and torsion. Okay, so let's look at the notch sensitivity. As I just told you, the bigger value or the highest value for KF, which is the fatigue stress concentration value, a factor is KT. In the KF is defined as a reduced value of KT. هو قيمة مصغرة من KT وبالتالي أكبر قيمة للKF هي KT. طب لو رحت عوضت هنا عن KF بKT تطلع Q كام؟ بواحد. اوكي؟ يبقى معنى كده for a fully notch sensitive material where KF reaches its maximum value of KT, okay, the Q will be equal to 1. طيب the extreme case حاجة بعيدة خالص على اللي احنا لسه قايلين ان انا عندي material very tough and very ductile, which means that it does not really it's not really affected by the presence of these notches. الماتيريال مش متأثرة قوي بوجود هذه النوتشز فيها. This means that KF will be equal to 1. Okay? يعني ايه؟ يعني ال stresses in notch specimens هي نفسها ال stresses in notch free specimens. فكأن عندي material لا تشعر بوجود هذه النوتشز. So if you substitute KF equal to 1 in this equation, the notch sensitivity will be equal to 0. So let's read this together. If Q is equal to 0, then the KF will be equal to 1. The stresses, both stresses are equal. And the material has no sensitivity to notches at all. This is a very tough and ductile material. On the other hand, if Q is equal to 1, the notch sensitivity is equal to 1. This means that KF has reached its highest value, which is KT. The KF is equal to KT. And this is the case for a fully notch sensitive material, a brittle material. Okay? Manipulating this equation will lead to this equation. So KF is equal to 1 plus Q into KT minus 1. لو انت استخلصت KF لوحدها من المعادلة دي هتحصل على هذه المعادلة. This is the equation that you need to know. دي equation انت محتاج تبقى داخل أي امتحان وعارفها. This is again for normal and this is for shear. This is another way of calculating KF, but we'll put this aside now. Let's Anova equation. Let's skip this slide. These two charts will be given to you. In the case of reversed axial or reverse bending, I'll be using this chart. In the case of reversed shear or reverse torsion, I'll be using this chart. This chart, based on the notch radius, okay, and the ultimate tensile strength of your material, you would be able to go into this chart and get the value of Q. As we said, the value of notch sensitivity Q ranges from 0. This is a very tough material, to 1. This is a fully notch sensitive material. Very tough and ductile, very brittle. So knowing the notch radius, which is related to the geometrical discontinuity present in the component, a notch radius, knowing the ultimate tensile strength, I would be able to go and get Q. الخطوط السوداء دي خاصة بالستيل for ultimate tensile strength of 1.4 جيجا يعني 1400 ميجا 1000 ميجا 700 ميجا 400 ميجا باسكال. خلاص you would go and get the Q. and the dotted is for aluminum alloy. Okay. The same here, knowing the notch radius, this is for the reverse torsion. Knowing the notch radius, this is for quenched and drawn steel, this is for annealed steel, and this is for aluminum alloy. Knowing the notch radius, you would go into the respective line that suits your problem او المناسب للمسألة بتاعتك وتروح تجيب الكيو شير.